just to tell you that indeed, also in this confined case, in the case which is closer to many practical systems, you can explain the switching that takes place, the various modes that you are triggering, the fact that you start with a given mode, mode 2, for example, you move to mode 1, or that you have this sort of, you go from one frequency here, a high frequency, to a low frequency. You have this sort of different possibilities here. You start with a high frequency, and then you fall on this low frequency here. So all this is very nicely explained by this describing function. All right. So this has been used. So we use this framework, for example, to study these unconfined flames. We use the same framework in another configuration that we studied with Paul Paliès, and in this case we wanted to actually to see which configurations were unstable, which were stable. And we use the describing function as well. And by changing, in this case, it's a little more difficult to change the burner. So you can change the size of the burner. You can change, you don't have the piston. So that's, but you change the size of the burner. You change the length of the chamber. And you can actually say these places are stable. These are unstable. These are very unstable. And you can actually predict that using the describing function. The predictions are reasonably good and not perfect. We had 24 cases, and a few of them were not very well predicted. So, we did also extensive studies of this configuration, which is generic: a manifold, the injector, and also the chamber. All right, let's. There are still issues because many situations you don't have a stable amplitude like that. This is a very nice limit cycle, but very often you have something which looks like that. When you look at the frequencies, you have the fundamental frequency, but you have also subharmonics and harmonics of this fundamental. And if you plot that, for dynamical systems, it's nice to plot this in 2 or 3 dimensions to see what the trajectories of these limit cycles look like. When you have a stable limit cycle like that, it's essentially, so what you plot here is the pressure, and the pressure with a certain delay. And you see something, it's a trajectory like that. When you get to this unstable limit cycle, or a limit cycle which has also amplitude changes, you get something like that. And there are cases where the amplitude does this sort of very strange oscillations. And it becomes, so here you use a 3-dimensional plot for this system, and you cannot scramble that, but it looks like that. So you have something which is, when you hear it, it's not very nice, and what you have is something a little more complicated. And this is, of course, not very easy to represent using this describing function. So, so you have these other cases that are that require additional work. You have some galloping limit cycles. You have some. These are the very stable limit cycles, but then you have these very, very different types of limit cycles. There are cases where you have actually 2 frequencies together. For example, in this case, you have these 2 frequencies. So we studied some of that, but this is really too detailed. If you want, you look at the papers that we wrote on these subjects. We found certain conditions where you have this In some conditions, you will have mode switching. You will not have the two frequencies at the same time. In other conditions, you have the two modes coexist. And we wanted to know what were the criteria for this coexistence. And apparently, it's the trajectories. In this case, the trajectories have the same behavior, while in this case, you have one is going up, the other is going down, so you have switching. So this is a configuration where you may have two modes, while this one is a configuration where you have switching. All right, let's drop that. And now, are there any questions now that on this describing function techniques? So, anything? Let's now move to combustion control. So of course, we learned a lot about these combustion instabilities, and this is a prerequisite if you want to control flames. If you do not understand what you have, it's very hard to control. But now we have a good knowledge of things. We know that the acoustics is very important. We know how combustion responds to acoustics. We know how to bring things together. We have instability models. We've seen this concept of transfer function. And so now we have to use that for controlling. So what are the possible concepts here? So you have the situation in general is that you have a resonant system. So acoustic energy, you have a balance of acoustic energy. You know that for the resonant modes, you may have problems. You have an acoustic gain of the combustion process that can be described by the transfer function, describing function. And you have acoustic losses essentially at the boundaries. There are many possible losses. You may have just radiation outside from the burner. You may have friction at the boundaries. You may have damping by transformation from acoustics into vortices. For example, you transform an acoustic wave into vortices, and these vortices dissipate, and so it's a damping process. So in general, what one wishes, what one can do is to enhance the acoustic damping. You bring the damping to a higher value. You have the gain here, and if you have sufficient damping in the system, it will be stabilized. So this is a way to control your system is by just increasing the damping. What helps you increase the damping? Helmholtz resonators, quarter wave tubes. One simple method is to, the resonant possibilities, and you fit a quarter wave tube. You take a tube which has a dimension, so you have your combustor here, and you place a tube which has the quarter wave size like that, so the length of this tube is lambda over 4. And this is, of course, where is the damping taking place? Essentially at this place here. So there is damping just due to the motion that is produced here. And so how do you do that in practice? Sometimes you just place a piston at that point and move the piston until the system becomes stable, and you know what is the size of your. So of course the diameter here is not well known. If it's a very small diameter, it will have no effect. If it's too big, it's not good either. So you have to find what the diameter is, but that's a simple technique. We've used that. It works, you know, just you work like a trombone and you get your damping at the right place and you eliminate the oscillation. Another idea is to have flames that are that will be neutral to oscillations. And this is what I'm going to tell you a little more about. The idea is as follows. You want, for example, when you have a collection of flames, that they respond to oscillations here in opposite phases. This is about what we want. This is calculations. You send the perturbation here, and this one is going in the opposite direction. It's not perfect, but it's something like that. So is it possible to get something like that? Well, it is possible by just placing an orifice here, and you have a distance between the two, and you get something like that. This is a calculation of two flames. You have to imagine that you have a very large number of flames. So you do this. We call that a dynamic phase converter. And by using that concept, the flames respond. If they get a perturbation, they respond in opposite directions. So in the mean, there is no heat release fluctuation, or it's very little heat release fluctuation. So you can tailor your gain in this respect. This is shown here. You see you have these flames, which you have acoustic waves coming from upstream here. They impinge on the flames here. And because this orifice is displaced with this one, the phase is different. And when one flame goes up, the other goes down. Not exactly, but something like that. So you have to imagine a big collection of such flames. So this is in this paper, and I'll give you a little more details on that. The technique is here. You see when the two flames, all the flames, when there is no such system, all the flames act together, and this is the dynamics. When you have these two flames with this equipment, you get something like that. And this will have, essentially, it will have a very little fluctuation in the heat release rate. The heat release rate will remain essentially constant because of this motion of the two flames. Another way of looking at that is to use active control. There has been a lot of work in this. The idea is you have this loop, flow, combustion, and acoustic feedback, and you're going to place another loop. So the system is like that. You put another loop with a controller here and send here back perturbations in the flow using an actuator. And like that, you have a way to modify this loop here. So for a number of years, we've worked on that. It's possible to demonstrate that in various situations. Actually, these concepts date back to the early 1950s. If you look at the literature of people working with the sensitive time lag, they were considering systems of that kind. What you see here is Tien and Frank Marble at a later time in China. So for example, Marble in 1953, Tien in 1952, and Croco as well were considering reducing the rocket engine instability using a sensor. You put an amplifier, an actuator, and you act on the fuel and the oxidizer, and you can modify the stability of the system just by an external loop like that. So these concepts were already present very early this is not at the age where this corresponds to a much more recent photograph. So, in combustion, this there were no demonstrations of that concept in practice until much later. The early ones were made at Cambridge by Bloxage, and we also began a lot of work in this area with Thierry Poinceau. We demonstrated that it was possible to actually do adaptive active control, to use adaptive loops that would just adapt to the situations, because combustion is not a simple system. It's not something very the parameters change and so on, and if it's not adaptive, it doesn't work so well. So many studies were done in this respect. You see in developing algorithms, developing actuators, control loops. For example, this is one case where you have a combustor with injectors here. So you have an actuator with essentially like a driver unit or a Moog valve. This is what we used also extensively. You have this adaptive controller, and you need a sensor that can be optical or acoustic. That is, you use the pressure signal and you try to minimize the pressure signal, or at the microphone, which is here, or the microphone, or the photomultiplier, which is here. So you use that signal to send something to the actuator, and the actuator will act here and modify the injection. This is what we did on a more recent injector. This was a liquid fuel injector, swirling injector. So we had an actuator which was a Moog valve, and again we use the microphone signal through a filter control, and we modulate this Moog valve. Now the problem with this valve is that it goes up to 400 hertz. It's the band is limited. But it's powerful, so you can. And such systems have actually been implemented in gas turbines. So there was a gas turbine by Siemens, which was unstable, and the only way to get to the nominal power was to actually implement something like that. So it's pretty courageous to bring something which was in the lab and bring it to a big piece of hardware, put the actuators, there was a controller, it's a Moog valve here, a special mounting of this valve, and you use that to control oscillations in this gas turbine. So the person who did that is Herman. And so in principle, that is possible. It takes a lot of hardware that was done, but you don't want that. In general, it's a little too complicated for hardware. So if you cannot do otherwise, this is one possibility, but basically you shouldn't do that. A lot has been done in terms of analysis, trying to analyze this sort of things. Of course, you replace combustion by a low-order dynamical model of the types that we've being developed. For example, the one on the low-frequency rocket instability, and you add a loop, and then you do controls. You apply your knowledge in controls. Everything is represented as black boxes. So combustion is a black box. Acoustics is here. You have the actuator, which is a box, the sensor, the controller. You can, of course, use these transfer function concepts using Laplace transform or Fourier transforms. You can go to these adaptive techniques, and it's very subtle. In fact, apparently it's easy. The idea is you have a filter here, and the coefficients of this filter are adapted so that you minimize the signal that you don't want. You don't want pressure fluctuations, so you minimize the level of pressure fluctuations. But there are subtle things. For example, you have a direct pass between the actuator and the sensor, and this has to be included in this analysis. The actuator will directly influence what is seen by the sensor, so you have to include that. So you have to identify this pass first. So the system goes through first an identification of this pass, and second, you use these adaptive control techniques. One question that we were also interested in, is it possible to actually use a Navier-Stokes solver for combustion right here and implement a control loop and go like that? So, and this hasn't been done so much. So instead of doing experiments, you do the calculation and you put a control loop and try to see if you can control your flow. And what we did, at one point, we had big problems with this rocket engine oscillations, low-frequency oscillations produced by the baffles, which separate the solid propellant. You have solid propellant here, you have baffles, and these baffles protrude in the flow, and there is flow here, producing these vortices. These vortices impinge on the nozzle, they produce pressure waves, and this resonates, and you have more vortices synchronized here. And the idea was to inject some oxidizer, because all of this is a reducing ambience. So you inject oxidizer using an adaptive controller in order to reduce this vortex shedding and impingement on the nozzle. And this is exemplified here. You see you have vortices which are here and impinge on the nozzle, producing pressure waves. There are other types of vortices. For example, they are produced at the edge of the solid propellant, and they impinge on the nozzle. And you even have vortices which are just produced from the surface of the solid propellant. There is if you want to know the frequency of this process, you have a famous result by Rossiter, which tells you what is the cavity resonance of such a situation. And you can say that the period of the oscillation multiplied by a certain number, which corresponds to the number of vortices, is equal to a convective time, an acoustic time, and some sort of time which represents the interaction between the vortex and the nozzle. And if you consider that delta t is a fraction of the period, you get finally a frequency which is like that. So it's a coefficient, let's say 0.6, for example, the velocity u in this system divided by the size of the cavity. M is the number of vortices minus alpha is this quantity here. It's a factor that you don't quite know, and the Mach number also appears here. So you have an idea of the frequencies of these configurations. And what we did, of course, it was too difficult to make it in a real rocket engine, solid rocket. It's very expensive and so on. It's even expensive in a small solid rocket engine. So what we did is first try to do that in a simpler configuration which has some of the features. You have here a baffle, you have the nozzle here, and instead of injecting reactant, you have a loudspeaker. And is it possible to control the vortices in this cavity using this active control using a control algorithm? So this is a paper that we published on that. The experiment was done at the von Karman Institute in Brussels. So we brought all our system, our electronics and adaptive controller, and we brought it there and plugged it on the system, and it worked. So you have the system is oscillating at various frequencies. These are the modes of this system. You can see it reaches pretty high levels in decibels, 136 decibels in these regions. This changes as we change the velocity inside the system. And by putting the controller and operating the controller, you see that the levels are much lower here, even there. There is a little bit here, but basically you eliminate these. This is brought down. It's also interesting to try to see if that can work using numerical work. And the difficulty is that you have to implement that. In this time, you have to bring in sources, which will be the actuator, and implement that into a Navier-Stokes code. That's what we did. And what is important is that if you put a source of reactants here, you should not forget that the source will also have some energy. If you forget that term here, this is very bad. So if you don't forget it, if you place it properly, you put here, the actuator is injection of reactants right here. And so the organization of the system is as follows. You have this Navier-Stokes solver here. Now this operates at a very high frequency. The time step is very small. And then you need to have the signal here, but the signal comes at a very high frequency, and you have too many samples. So you have to make here, to pass it into a low-pass filter. If you don't do that, it doesn't work, because this will not work at 4 megahertz. This is good for the calculation, but for control, you operate at a much lower rate. So you pass that into a low-pass filter, and then you do your control algorithm here, and what comes out is again it's a signal which is sampled, and it's useful to have here a low-pass filter, not to send these little things because it will be bad for the calculation here, and you bring that in through the actuator sources. And you can actually do this loop numerically. And that was what was done. You see the mismatch between this frequency and that frequency deteriorates the simulation. And the problem is suppressed by this is what we learned. At the beginning, we didn't care so much. We just took the signals here, sent them to the same control algorithm that we used in experiments was used here in the calculations. And then we send them again to a low-pass filter here, because it's important to low-pass filter the inputs and outputs of this control method. And what is seen is that the signal is here, so you have a good oscillation, and by putting in the controller, it takes a little while, you get to this level of oscillation. You cannot get rid, at least in these calculations, we were not able to get rid of all the oscillations. But you certainly, after a little while, it adapts, and you get a small you get a small level, much smaller than what you began with. And what happens is basically you start with vortices which are like that, and you change the structure of the flow inside the cavity. And this one is less resonant than that one, so the level of fluctuation is lower. It's a first exercise in trying to do active control as a loop on a Navier-Stokes solver, on a calculation. So that was, of course, we haven't gone to implement this system. It wasn't sufficient. It works, but if you look at the difficulty of implementing that, it's too difficult. So you have to design the engine so that you don't have this, so that the vortices are not too strong, and so that the oscillations, because these oscillations produce vibrations, thrust oscillations, and the whole rocket is vibrating at these are very low frequency events. The frequencies here are much higher because we did the calculations in a smaller device. All right. Do you have any questions on these? Yes.
So, one more slide you have shown the CFD simulations.
Yes.
You mentioned no thickening factor.
No?
Thickening factor.
Thickening. So in this case, the question is about the thickening factor to represent the flame. In this case, it's essentially a flow problem. It's vortices. Combustion takes place close to the solid surface, and what you see are vortices which are developed in the flow, and which are essentially so what we are controlling here is the flow itself. It's the flow of burnt gases. We do not represent the combustion itself. Yes. So the code is the code Sierra here is developed by Honora. It's the French aerospace lab, and they have done extensive studies of this low frequency rocket instabilities, segmented rocket engines, where the problem comes from the fact that you cannot make a solid propellant of the size of the rocket. You make it by a certain volumes, and then you put a baffle, and the baffle itself doesn't burn quite at the same speed as the solid propellant. As a consequence, usually it protrudes into the flow. It enters the flow, and the flow is rather fast, and you get these vortices. And the vortices, when they impinge on the nozzle, send pressure waves. And what you want to do is to reduce these pressure waves, because the pressure waves then will give thrust oscillation. The whole thing will exhibit vibrations due to thrust oscillations. Low frequency, not very high frequency. It's in the low frequency range because these are very large scale systems. And so this was a tentative study of what could be done with active control. Of course, the difficulty is to put in an actuator and the sensor somewhere. The sensor can be done. The actuator is a different stuff, and then the result is not what we would have liked to get rid completely of the thing, and it doesn't. It changes the number of vortices, it changes the frequency, but it reduces the level of oscillation, but not to a sufficient amount. But what we learned here is how to do that numerically. That is, you have a Navier-Stokes code, and you put a control loop, and you control the flow numerically. Everything numerical, so this in principle is cheap. doesn't require a big experiment, but at least that's what you should do before trying a really complicated experiment. What we've done here is also we did some these experiments at the Front Common Institute were representative in the sense that you have the vortex structures. We were able to control that. Again, a gain of 10 decibels was obtained, 10, 15, which is pretty sizable. You could hear it, you know. It's quite nice. You get a drop in the level of oscillation. So definitely you control the flow. Yes?
So the flow control is basically affecting changing the vortex changing.
Yes.
Is it affecting the combustion?
So in this case, not so much, you know, because combustion is taking place in a very thin layer close to the boundary of the solid propellant. And what we do here is we act more on the vortices. We try to counteract the pressure waves that are obtained from the vortices impinging on the nozzle. So, and then if these waves are of lesser levels, the vortices will be of lesser amplitude, and the process will be brought down. The level, the amplitude level will be lower. So it's so active control has possibilities, but the implementation is difficult, and also you know when you have an active element, what happens if it doesn't work? You know, so it's better to use passive techniques. So the passive is essentially damping. You know, but sometimes it's very difficult to have damping. The problem is that damping is not too easy to implement, especially if you have problems of weight. You see a quarter wave device may be adding weight, and if you're on the ground, if it's a gas turbine, yes, you can put Helmholtz resonators, quarter wave devices. If you are in an engine, it's less easy, so you need, so there are other ways. For example, you have perforated plates which are polarized by a flow. These are very effective in terms of introducing damping. All right, let's move to, let me show you a little bit of the other idea, this idea of changing the gain of the process. Sorry. So what I want to discuss now is this idea of being able to have the flames less susceptible to perturbations. This is based on the work of Nicolas Noiret. He is now a professor at ETH in Zurich. And okay, the whole background is flow, combustion, acoustics. We want to control that. The solution, active control, we will discuss that. Passive control. In terms of passive control, you may enhance losses at the boundary. You may put baffles. For example, in the F1 engine, the final configuration of the F1 engine had baffles. You see, you have baffles here. And this break the resonant, they reduce the resonant levels of the most destructive modes. So this is the final configuration that was implemented in the F1. of course, one thing that we would like to see, is it possible to reduce the gain of the flame? And the idea is, again, we want to reduce the gain. This is the strategy, is to modify the gain by acting on the flame dynamics. So what we use is this device, and the idea is that we would like to have these flames operate in a different manner, desynchronize their operation. So you remember this is a stable regime, and in the unstable, the flames are oscillating strongly in this direction. We've seen that a few times. This is stable here first. And if it's becoming unstable at this frequency, it's like that. So you have this. So this is what we would like to control. And in this case, we don't want to use passive techniques. We know that this is a possibility. We want to use something which is not also active control, because active control has these difficulties, implementation. So that's the mechanism that we want to modify. And what is visible here is that all the flames act in phase. They are all together. They produce this heat release pulse. So the idea is to have the flames moving in a different manner, modify this. This is all synchronous. They shed this strong pulse of heat release. So we want to change that. This is the behavior that we have. We have unstable right here. There is a very small stability region here. All right. And make use of the multiple flame configuration and try to avoid the coherent response. Now, if you want to change the behavior of the flames, the acoustic wave, the delays that you can get in acoustic waves are very small, because the speed is the speed of sound. So you cannot have big delays. Acoustics doesn't provide big delays. Of course, if you are on a very large distance, you have a good delay. But on a small distance, you are not able to do a delay. So the thing is to transform the acoustic perturbation, which impinge on the flames, to hydrodynamic perturbations, vortices, which propagate at the mean velocity. So this is the velocity is much lower than the speed of sound. And then you can change the phase with a much better capacity. The idea is to be able to change this phase. So this is what we invented. Actually, it was patented. You have an orifice here and an orifice there, and you just include these orifices in this channels. And what you do is that this produces vortices, and the vortices here are, because you have this distance, you have a delay which corresponds to this distance. And these vortices will impinge on the flame, and you will have situations of that kind, and then situations of that kind at half the period later. And so when you have the acoustic perturbation, you make here a phase conversion. You include a phase due to this process. And so and it's very simple. You just put an orifice, and the orifice converts your acoustics into a vortex mode. And the vortex is then advancing at the speed of the flow. So the acoustics was at the speed of sound. The vortex is at the speed of the flow. Does that work? Yes. You see, instead of having, yeah? to suppress the resonant coupling. So how do you determine this phase? Well, you have the phase is equal to omega times delta L divided by UCV, the convection velocity of the vortices. So delta L has to be equal to UCV divided by 2F to have a delta phi of equal to pi. So that's it. It's very simple. The idea is very simple here. You put these orifices, they are displaced by delta L. And half of the flames have one or a type of orifice, the other half have the other type. So now the first thing to know, is it really true that you convert acoustics into vorticity? And this has been verified. We can definitely verify this, for example, doing calculations, but also in experiments. For example, we build this experiment. You have a loudspeaker at the bottom, you have the orifice, and you see the vortices very clearly. So you put a simple diaphragm in a duct. You see you have the duct, you have a diaphragm here. You arrive with acoustic waves here, U prime, and here you produce vortices. And these are not negligible vortices. They are very powerful. And these are the perturbations that will act on the flame. The flame would be here. And what you do here is that instead of having these acoustic waves propagating to this point, you have these vortices propagating to this point. And in the next channel, you put the orifice here. You make sure that the distance between these two is reasonable, delta L, and the vortices are shed here. And you have a phase between these vortices. And so this flame will be impinged by these vortices. And so it's very simple to implement. We did also calculations of these vortices. This is the grid that was used. It's a unstructured grid, and you definitely can see the vortices, and they give you the convection velocity. You can determine in this way the convection velocity. And we did also directly these calculations that I've shown before. This is not a simple calculation because you have laminar flames, so you have to calculate the laminar flames here, and you can do that. And you can see that these flames behave somewhat like what you want. There are some movements which are not quite what you thought you would get, but basically it does. So instead of having the two flames acting in phase, you have them acting in opposite directions. And this is it's a cut through these calculations. So this is how it looks like. We were very happy to do such calculations. Because it's not too easy, you know. It takes a little effort to have these flames, and then you transform the acoustics into these convective modes, and they impinge on the flames. And now, does that work in practice? This is what we did to control this frequency of about 660 hertz. We have this. So without the system, with the system, sorry, if you do LDV at these points here, you do see that the two signals are exactly out of phase. So the flames will respond with a pi between them. And what happens if you are off design? Well, still you get something like that. So one flame is going, one velocity is like that, the other one is like that. So of design, you will get something. It works even around the frequency of your design. And in principle, this will work. Let's see. Yeah, so this is what happens without any system. You just have all the flames move up and down like that. And so this will be unstable. It brings in fluctuations in heat release. And if you put this dynamic phase converter, which are essentially these two orifices, you see that the flames execute motions which are in opposite directions, which is emphasized by this straight line. It's nicer to, otherwise the eye doesn't see it so well. Like that, you see it better. And it is true that, so now these are made with the loudspeaker. You send an acoustic wave by the loudspeaker and you see the chemiluminescence. This is without the phase converter. And when you do the same, but you put the orifices and so on, you see the chemiluminescence is essentially constant here. So the intensity doesn't change so much because the flames are out of phase. And does that work for a situation where you have self-excited oscillations? Yes. This is the level of oscillation of the system for all these lengths here. And when you put the orifices, you are below. You see, you have the gain is about 20 decibels here. Sometimes it's less. But here it's on a fairly large scale of lengths. So basically it works. It suppresses the oscillation. There is still something coming in at a higher frequency, but at a lower level. The oscillation level is reduced, but you do get some high frequency here. So if we don't have the system, then you're here. Yeah. So it's simple. Very little requirements in terms of space. There is a minor modification of the injection geometry, and it's rather broadband effective. So you have a way to, it's a demonstration that by properly designing this injection system, you can actually reduce the gain very much. And then you reduce the oscillation. Some drawbacks. You have some head losses, and you have also the eigenmodes, which have other frequencies which may arise because you suppress the lower order modes, and then you may have another one which will occur. But basically, it has some advantages. So at least we thought we had a way to fix such instabilities. All right, what reactions, what questions? We got the silver medal for this paper at the Combustion Institute. That was, it was in the, you know, the silver medal is for the best paper at a given symposium. That was the symposium in 2008. And it was considered as a very original paper. I think it is. I think it's, I haven't seen such an idea elsewhere. So I think it was pretty original and effective. Yes.
Like you mentioned, there is a chance that with these new dynamics you can introduce maybe a new mode.
Yes, because you have all these other possibilities. You have all the modes that are here. So you eliminate one, but another one may occur because there is energy there, and you are not. Yeah.
Now there's a frequency to the shedding of the border.
Yes. Yeah. Basically, nevertheless, the system operates, but and the level is certainly decreased. It works when you go to the lab, but when you move away from the design point, you may have this higher frequency coming in. So you get another mode coming in.
Is the next step like introducing an active component to this maybe?
You don't want to put active control. Active control is really interesting. It's nice. You can do a lot of things with it, but it's difficult to implement in practice. So while this one is very simple to implement, you change the injector by putting diaphragm, small diaphragm. You produce these vortices, and they instead of having the acoustics directly attacking the flame, you have these vortices which are shed, which have a lower traveling velocity, and as a consequence, you introduce this phase. Yeah. All right, let's break for a quarter of an hour, if you wish.